Okay, today we are going to be talking about encoders and Spark Max controls and kind of the intro to how we control some of the motors we use in on our robots. We briefly mentioned encoders and things when we started talking about motors last week, but we're going to go through it a little bit more and see sort of how they work and why we use them. Because at this point, there's pretty much an encoder on every one of our motors now, so we use them for a lot of the control and just improving what our robot can do and making everything more efficient and fast for us and more precise. All right, so the rough idea of what an encoder is an encoder is anything that allows us to count the revolutions or partial revolutions of a rotating shaft. So if we want to know how many times something has spun around, we use an encoder to do that. A very basic encoder can be made from a disc with two colors on it and a light sensor that can tell the difference between like light and dark. So in this very basic example, we would attach this disc to a spinning shaft. You have a dark side and a light side, and we have a reflective light sensor pointing at it and pointing to like this spot with this where this yellow ring is. This is just representing where the light sensor is looking. So as it's looking at this spot as the shaft is rotating, you can imagine that sometimes the shaft is gonna be seeing dark, sometimes it's gonna be seeing light. And what the robot is able to see is basically a 0 or a 1. In this example, the robot sees 0 when it's pointed at the light side of the circle, and it sees a 1 when it's pointed at the dark side of the circle. So if we continue that and we assume that this disk is rotating, as it rotates, the robot would see a 0 for a while when it's on the light, and then when it switches, it would start seeing a 1 because now it's seeing the dark. It would rotate again, and then it would go back down to light. It would rotate some more. It would go back up to dark, and it would keep doing that as the shaft spun. So this allows us to get a basic idea that the shaft is moving, right? We can see these transitions from light to dark, and we can know the shaft is rotating. So let's talk about some of the terms that go into encoders a little bit. So every time we are able to like detect that change, we call it a tick or a count, because those are what we're counting when we determine how far the shaft is rotated. So it's how many times the processor, controller, computer, or whatever you want to call it, every time it counts. For this encoder, it's 1 revolution, but a lot of times there'll be, just every time it sees that change, right? There's a couple other things we have. We can kind of divide this graph up a little bit. So we have this line right here we call the falling edge, because it's the edge that we go from 1 to 0. So we're falling back down to 0. And then the opposite of that would be the rising edge, where we're going from 0 and rising to 1. So some encoders and some processors will count only falling edges, some will count only rising edges, some can count both. You can do a bunch of different, there's a lot of fancy different things you can do. But just know if you see those two terms, that's what they're talking about. For now, we can assume that we're only looking at the falling edge in our example here, right? So every time we see a falling edge, we know that that's 1 revolution, because we've gone through the half that was light, we've gone through the half that's dark, we go through the half that's light again, we go through the half that's dark, and now we're back to 2 revolutions. And so we have some idea of how many times this shaft is spun around. So if we wanted to use this to count like how far a robot has driven, we could know if the robot drove 1 revolution of the wheel. If this was mounted to like the wheel on a robot, we can know if it's driven 3 revolutions of the wheel, that sort of thing. The problem with that, at some point you can notice pretty quickly, is that 1 tick or 1 count per revolution isn't very precise, right? If we had this on our wheel, we could only know if we were going 1, 2, 3, integer number of revolutions of our wheels, and that's not all that useful necessarily. We may want to be able to go a quarter of a revolution or half a revolution, right? We want to be somewhere in the middle of a revolution and not just worried about single increments. So what you do is you divide the disk into smaller and smaller segments to get a higher resolution, right? So resolution is just like the resolution of a monitor. As you get smaller and smaller pixels, you get a higher resolution monitor, right? You get 1080p monitors up to 4K monitors. They have smaller and smaller divisions of the screen because they have more and more pixels. Each one of the little divisions is smaller. So it's the same thing with encoders. When we get higher resolution encoders, we're just dividing up that circle more and more and more to where we get more ticks or counts per revolution. So in this example disk here, we have 12 black and 12 white segments. So if we're still only counting the falling edges, this first falling edge is 1/12 of a revolution. And this one out here, which is the 6th, is 1/2 of a revolution, right? So we have a lot more. We could tell the robot to stop a quarter of the way through. We could tell the robot to stop half the way through, a 1/12 of the way through. We have a lot more. We basically have more information about how far this shaft is spun. Okay. But this leads to a problem, right? So if all you want to know, if the robot's just going forward and we just want it to drive forward and then stop, that's great. We can count in that way and we're done. But our robot doesn't just go forward, our robot also goes backwards. The two different sides of the drivetrain spin at different speeds sometimes. And so we're still missing some information. And one of the big pieces of information we're missing is direction. So with one sensor, the graph over here for going forward and reverse are basically the same, right? If the sensor is pointing right at this spot, we're looking at a dark portion like we are right here. If we rotate this disk clockwise, our next transition is going to be to light, even though if we're going, we'll say clockwise is forward. Or if we were here and we rotate it counterclockwise, we'll call that backwards or reverse, it's still going to be light. So we don't know, just based on which our signal does here, which way we're going. It'll always be from 1 to 0, from 0 to 1, no matter which way this disk is spinning. And so that's just not very good if we want to know if we're going forward or backwards, right? That seems really important for the robot to know that, and to be able to keep count of that so we can drive forward, back up, do what we need to do to be able to get to the spot we want to go to and kind of maintain an idea of how far we traveled. So we do have a way to fix this. And the way we fix this with encoders is we make slightly more advanced encoders. So instead of having this single graph and this single input, we build what's called a quadrature encoder. A quadrature encoder uses, it's basically like if you had two encoders combined. So you have two light sensors, you have two disks, and you just mount the disks in a specific way so that they're rotated a little bit past each other. So basically it's called 90 degrees out of phase. So you line up, which you don't need to really know what that term means, but basically you just line up this one dark segment halfway between this light segment and this dark segment on the outer ring, and you get the configuration that we need. And so in this picture down here, we're looking at this first sensor is looking at this orange circle, and this second sensor is looking at this blue circle. These are roughly right in line with each other. That's what they're supposed to be. Forgive my PowerPoint drawings if they're not quite exact. And their graphs are going to look a little bit different because they're pointed at the two different spacings on these two different circles. So while this disk rotates, we actually get a potential for 4 different states, which is why it's called quadrature. Quad equals 4, because you can have either both these sensors could be seeing light, right? They'd both be 0. you could have both of these sensors seeing dark, or you could have sensor 1 seeing light and sensor 2 seeing dark, or you could have sensor 1 seeing dark and sensor 2 seeing light. So there's 4 different possibilities for what these 2 sensors could be seeing. And with that, this allows us to tell direction. And we can look at that in a little bit more detail here in a second. So the way we can tell the direction is by basically having one is like kind of our primary sensor. So let's assume orange is our primary sensor, and we're still basically counting every time orange goes from 1 to 0 like we were doing the whole time, right? So this falling edge, 1 to 0. So if we're up here on a dark segment and we're falling from 1 to 0 going forward, so we're going to go this direction, left to right we're going to call it forward. And when we do that, the computer, controller, whatever's doing the counting can then check on the blue sensor and see what value that is at that falling edge. So here we're at this falling edge. This is we're going down to 0 here. We're going from 1 to 0, and blue is already at 0 here, right? This is kind of in the middle. This line is supposed to be basically dead in the middle of this one, if everything was drawn properly. So we know going forward, when this goes from 1 to 0, blue is at 0. If we look at that same problem, but going in reverse, so now we're going the opposite way. So we're going from right to left. So if we were here at dark, and now our falling edge looks this way, right? We're going back down this side. We get a 0 on orange after we were at 1, and blue is up here at dark, so it's at 1. So that's how we can tell the difference. Is we have basically whenever we see a falling edge, we check what blue is, and if it's a 0 in this case, then we're going forward. If it's a 1, we're going backwards. And so this is what this slide kind of shows us. So as this disk is rotating, we can watch this, and it sees those different segments, and it sees how each one, this would be orange, this would be blue, how each one of these counts based on whether we're going forward or going reverse. And you can kind of see the sequence here where you always know from 1 to 0, blue's at 1, from 1 to 0, blue's at 0. So we can know if we're going forward or reverse, and we can adjust our count. So every time we go from 1 to 0 now, we look at the blue one. If it's 1, we subtract 1. If it's 0, we add 1, and we can keep track of how far we've driven, even if we're going forwards and backwards. Okay, luckily, we don't have to actually build these almost ever. I think we built one for our launcher wheel in 2012. We had like an actual painted disc basically and a light sensor looking at it. I don't think we've done that since then. So now almost all of our encoders are built into our motors. They have higher resolutions, and they work really well, but it is a good idea to know kind of how they, the concept behind what's going on and how it's actually determining the speed and direction of our shaft. Okay, so how do we actually determine speed? So we've talked about determining how many times it's rotated, right? So with how many times it's rotated, we can get position roughly. If we know the diameter of our wheel, we know how many times it's rotated, we can figure out roughly how far we should have traveled along the ground. Or if we need to know how high an elevator is moved or something, we can figure out how many rotations of the motor leads to how many vertical inches up and down. We can kind of figure that out through the gearing and different things that we've talked about before. But speed's a little bit different. So determining speed, we need to know, there's a couple different ways we can do it. We basically have to figure out some way to relate how far we've traveled to time. So there's kind of 2 different ways we can do that, and there's 2 different ways the computers or controllers do that. One is we can time how long it takes to travel a certain number of ticks. So it's kind of like if we were measuring someone and figuring out how fast they run the 40-yard or 100-meter dash. If they were really fast and they could run a 100-meter dash in 10 seconds, they would be averaging 10 meters per second during that time. We can do the same thing with ticks. We can say, okay, how long does it take us to get to 100 ticks? We can figure out how many seconds that is to do the division, and we have an idea of how fast we were going during that time interval. You can also do it slightly differently, which is we can measure how many ticks we travel in a set amount of time. So instead of setting a certain amount of distance and measuring the time, we can set a certain amount of time and measure the distance. So it would be basically like telling someone to run for 100 seconds and then measuring how far they ran. So if they ran 600 meters in that 100 seconds, you could do the division again, 600 over 100, and you would find out that they averaged 6 meters per second during that time. And we could do the same thing with ticks or revolutions or whatever we wanted, however we wanted to measure it for the encoder time. Again, luckily we don't have to do any of that, so we're not having to like write that specific code to figure out what the time is or anything like that. The motor controllers, RoboRio, whatever we're plugging our encoders into, do all of that for us. And they're computers, so they can do this on a much, much smaller time scale, right? If you're sitting there with a stopwatch, there's only so fast that you can click and unclick the stopwatch and still get an accurate reading. And there's only so much of a distance we can actually see accurately or measure accurately. With the encoders and the motor controllers, they're able to do it in milliseconds instead of seconds, so we can get a much more accurate, close to instantaneous idea of how fast we are going. Most of the time when we're talking about speed of a motor, we're going to be talking about RPM, which is revolutions per second, or sorry, either RPM, revolutions per minute, or RPS, revolutions per second. This should probably be minute, because that's most of the time what we're using. I'm going to fix that because RPM is just more intuitive. A lot of people use it in all sorts of things. Baseball, your car, tachometer is an RPM. There's a lot of things in RPM. Okay. Moving along to the next part of what we're going to talk about today. So the Neo is one of the motors that we discussed last week. It was the first brushless motor that really sort of mattered in FRC. It gave us a lot more power for a much smaller weight. And the reason we're talking about it is because it's what we're going to demo to show you kind of what an encoder can do and what the results are from it. So the encoder for the Neo is actually built in, so we don't see it in here. It's inside the casing. It has 42 counts per revolution. So for every time we spin this once around, the computer sees basically 42 ticks. So that works well enough for every FRC application we have. It's controlled by a Spark Max motor controller. The Spark Max looks like this. And basically what it's able to do is it's able to read those encoder values from the Neo. So it's able to see and determine whether it's seeing a 0 or a 1. Let me back up 1 second. I forgot to mention one thing. The Neo, instead of using light like the examples we were talking about, they actually have magnets and sensors that can see the magnetic field. So it's basically doing the same thing, but instead of seeing like a reflection of light, it just has a sensor and magnets that are swinging around, so it can determine whether the magnet is next to it or not next to it. And it still gets these same type of graphs, just using a different way to sense that rotation. So it's just using magnets. In theory, you could build an encoder off of anything that can give you the same 0 and 1 measurement precisely. There are some mechanical encoders that actually kind of almost like hit a switch or connect two things, that type of thing. Light, there's all sorts of ways you can do it. The light model is just the easier one to keep in your head most of the time, because it's easy to kind of imagine how these disks work with the encoder. Okay, so the Spark Max is able to determine the number of rotations for the encoder, so we can see how far the motor has traveled. It's also able to determine how fast the encoder is rotated. one of the reasons why we're going to look at the Spark Max today is it has a really cool feature in that you can plug a USB-C cable into it. Over here down at the bottom, we'll show you in just a second, there's a USB-C port. You can plug it into the Spark Max. You can plug that into a computer, and then you can actually control the Spark Max directly from a computer with some software that they have. The software is the Spark Max client. So you're able to download that. If you have a Spark Max and a Neo or another motor, you can set it up and actually control it, which we're going to look at today. So the Spark Max client is also how we do a couple different things with the Spark Max. It's how we configure it. So we pull this up and we use this every time we're setting up a new robot or we need to change something on the robot. We pull this up and we actually plug the USB cable into the Spark Max on the robot. And it lets us update the firmware. So the firmware is the kind of the base software that's running on it. So a lot of times they'll give us, they'll update the firmware to have new features, or they'll find a bug and we have to update all the firmware. So we'll do that on the robot using the Spark Max client. It's also how we set the CAN ID. And CAN ID is how we're actually able to know which Spark Max we're talking to, because they're all connected to the robot over the same CAN bus, those green and yellow wires we talked about a few weeks ago. And because of that, if you just had them all connected and you just said, hey, Spark Max, do this, you're not knowing all of them would do it if you don't have a way to determine which one you're talking to. So the CAN ID is how we do that. In this window over here, this CAN ID is set to 22. And so you can set them anything you really want. We never set them to 0, and we normally assign them kind of based on the subsystem. So our setup normally has like 1 or like 10, 11, and 12 as one side of the drivetrain, 20, 21, and 22 as the other, and then we'll move up. Maybe the intake is in the 30s, something like that. So we have some way of differentiating what they are relatively easily. But they don't really matter. You could set them to any number. We just make a system so we have some idea of what they are. You can configure the Spark Max a little bit too to tell it kind of what it's connected to. So there's brushed versus brushless mode. If we're connected to a Neo or a Neo 550, it's always in brushless mode because that's the type of motor it is, and that's how the electricity that it needs and the way it needs to control it is all determined there. So it's very important to make sure that stays in brushless. Almost all the motors we use on the robots are brushless, so that's almost always going to be brushless now, especially if we're doing it for a robot. There may be some other project where we're using a brush motor. Some of the things we talked about last week and some of the settings that we can control with our motor controllers, the idle or neutral mode that lets us set the brake or coast is set in here. And we can look at what the difference is in that in just a second when I actually do some demoing. And there's also a ramp rate feature that you can set. There's a whole host of other things, and there's a lot of settings. It's one of the things we're going to look at in just a second. Is there's a lot of settings. The run tab is where we're going to spend a lot of time, and what most of next week is going to be on as well, not just this week. We're going to introduce it here, but next week we're going to dive a little bit deeper. The run tab is where we're actually able to tell the Spark Max to actually run and change a bunch of the settings and have it do the different things just like if it were attached to the robot. So we can see, and we can actually, there's a graph here, so we'll be able to tell how far the robot has, or how far the motor has spun, or how fast it's spinning. We'll be able to see all of that on the graph. Okay, so let's look at how the Spark Max and Neo are actually set up. So I have a Spark Max and a Neo sitting in front of me. So we can see a little bit about what they actually look like and how they all work. So this is let's start from this end. So this is the power input to the Spark Max. So these black and red wire on this side of it, where it says voltage plus and voltage minus, are our power input. So this is right now just coming from a 12-volt wall supply that I have hooked up to these connectors right here. These are called Anderson connectors. We use these for almost every electrical connection on the robot. I can actually unplug it and kind of show you what the inside looks like. So there's little metal contacts on the inside. Ooh, I'm glad I unplugged it. One of these is a bad connection. This is we can stop and see. So you can see on one side, that little tongue is up there fully and locked in like it's supposed to. The other side has gotten pulled back, which means it has a really loose connection. So it may still work some of the time, but this is one of those key areas that is really bad if we ever did this on our competition robot, because basically at some point, probably in the middle of a important match or something, the robot would get hit in just the right way, or somebody would have moved something before the match, and this would unplug, and then our Spark Max, instead of doing what it's supposed to, running the intake or the drivetrain, whatever it was doing, will no longer have power, and our robot, whatever that feature or function is, wouldn't work anymore. So we always want to make sure that that is fully pressed in. I may have to find a screwdriver or something to do that. Let's see if I can get it. Basically, we just have to shove that back of that wire in a little bit harder. Let's see. So we can see, so this is the connector that's on the inside of it. This is the crimp connector that gets basically squeezed onto the wire itself. All of this silver that you can see is the connector, and it gets closed over. And it's just not quite what we want. It looks like it's okay. There might be a little bit of a tab there. I'm gonna unloop it and see if I can get it to do what we need it to. Maybe. Okay, well, I may not be able to fix it right now. I will remember to fix it before we get going any further, and especially before we ever put something like that on the robot. But I don't have a screwdriver next to me, and it'll take me a second to go up and get one. Okay, so the back of this has the USB-C cable. So this cable right here is plugged into my computer, and it has a USB-C port. So that's just where we connect that. And then these are the CAN bus wires. So these would connect to the other Spark Maxes in the robot, or any of the other things that go on the CAN bus. So if we had other motors like a Falcon, they would connect together too. And you basically go from each device on the CAN bus to the next. So you'd have like this going to the start of the bus and this going to the end of the bus, and you would just keep going and wiring them together over and over again. On top of the Spark Max, we have a few different things. We have an LED. So this is our diagnostics LED. So as we're doing stuff today, you can look at the color of this. It'll change whether the motor is spinning forward or reverse. It'll change based on what type of motor it's connected to. So if you're in brushed mode or brushless mode, the colors will be different. If there's some sort of error or something's not connected properly, it'll change colors. It'll blink in different patterns. There's several different things. A lot you can tell based on what's happening with this LED. This little cover right here connects another little port. You're able to plug in other sensors and some other devices into the top of here. There's little tiny pins in there, and a special cable that plugs into it. We keep it covered so they don't get damaged, or they don't mess up the controller at all if something were to fall in there, some other types of metal or something to connect pins that shouldn't be connected. We don't want any of that. So it gets covered. There's also a reset button. So in that little hole right there, if you stick a paper clip, you can reset the entire Spark Max back to its default settings in case someone had configured something that you didn't need to, or you weren't sure if it was configured properly. You can do it here. We can also reset it in code, which we do pretty regularly, normally right at the start of the match when we start up the robot. The other side of the Spark Max has our encoder cable coming from the Neo itself. So the Neo's over here. It has a encoder cable coming out of it, and it has these 3 motor power leads coming out of it. The encoder cable is in this kind of like sleeve. The encoder cable is in this little sleeve. It's a little bit to protect the wires inside of it, because these wires are super tiny. And they're pretty delicate. So these are one of the important things, is not like bend these too sharply or to pull on these wires, because you can pull them out of that housing. and show you what the connector looks like. You have to be kind of careful as we pull the connector out of here. You don't want to damage the wires at all as we do this. You kind of rock back and forth and it'll slowly start to come out. Hopefully I don't mess it up as we're doing the training. There we go. All right, so that's kind of what the connector looks like. It has all of its wires nicely in place. We can actually see the light changed here from a different color when we unplugged the encoder. So it's basically one of the error messages. And I can plug it back in. That's what the socket looks like right there. It does have, let's see if we can actually tell on here. There's those two little tabs up at the top of that tell you what direction it goes. Those go up, those point up when we're plugging in. It doesn't let you plug it in backwards. So you don't have to worry about that. So I'm gonna get that and get it back in. Then you kind of just push with your fingernail and kind of seat it all the way in there to where it's nice and firm and not coming out at all. And nice and stuck. Okay. Second, we have our, these are the 3 motor output wires from the Spark Max. We have Andersons again. We use purple and white for most everything on our robot, where red and black would be, just so they're color coded. We also know if devices are ours or not, if they have purple and white. Most other teams don't. But I did leave to a little bit of a problem, as Neos use a white wire as the 3rd wire, and we couldn't just put a white Anderson housing over there since we already have white on our red. So we use gray on our white Neo wires. But as long as they're all the same, it doesn't really matter. Even if the housing colors were different, it would still work, right? The color of the housing itself doesn't do anything. It's just there to help us identify what plugs into what and how it all works. And these kind of get stacked up. We would, there's actually remnants of cut zip ties here from when we took this off of something. We would run zip ties through these little holes in a loop, and they lock it together. So then when it's on the robot, no matter what happens, these aren't going to come apart. Because just like if the encoder wire or the Anderson on the other side or anywhere else, if any of those come apart, any single one of those connections, that motor no longer works. And then we're not driving or intaking or moving our elevator, or whatever that motor was doing isn't going to be doing that anymore. Okay, so last, this is the Neo. I do have a little bit of duct tape wrapped around it. So this is just so it's a little bit easier to see how it's rotating when I start spinning it up. So that should make it easy enough. And then I'm going to change my window size here a little bit. Let's see what we can do. All right. All right, that should work. So I need to get connected. So this is the Spark Max client. So I refresh, it now sees that there's a 22 Spark Max there, but I have to tell it to connect. So I'm gonna click the connect button, and it's going to pull everything up. I have this, this is the basic tab. So this is where I'm able to kind of change a variety of different settings on it. Some of them we don't need to go over right now exactly what they do, but there is references and things you can look up, or if you can start reading through exactly all the different settings. So there are some times where maybe it's like, oh, this system would benefit if we changed, if we use the soft limits or something, right? That could happen. But for right now, we're going to look at some specific things that we're going to edit. So we're going to actually use the run tab. There also is an advanced tab that you can go through every single setting in the Spark Max and you can edit it. So if we need to configure it in some different way, or we need to check how it is configured, we can look at it and do so in here. But the run tab is really where we want to spend a little bit of time today and more time next week. We'll be able to actually spin up our motor a little bit. So one thing, I don't have this motor mounted to anything, right? So it's just sitting here free. If I just spun this up at full speed, right now, it would jerk and almost like jump off the table a little bit. We don't want to do that. So I'm going to spin it up pretty slowly to begin with. So over here, this is where you actually tell it to start moving, but you can do that in a few, you can do that in a couple different ways. There's some settings before you can do that. There are a variety of ways you can control this motor, and this is what we're going to look at some of next week and today. The simplest is what's called percent. So the percent mode just sends some percentage of the voltage from the battery, or in this case, the power supply, to the motor. So it doesn't know anything about what's actually happening to the output of the motor. It doesn't know how fast it's spinning. It doesn't know how far it's going. It just knows it's some percentage of the voltage available is going to go to the motor, and that's going to make it spin at some speed. So if we put a smaller percentage, it spins at a slower speed. If we put a higher percentage, it spins at a faster speed. Negative will make it go reverse. Positive will make it go forward. And we can kind of tell it where it is. So right now it's telling it to go to 0. So if I tell it to run at 0, it shouldn't move at all. You may have noticed though that the LED changed. So when I stop it, the LED will be flashing. So that means that there's no signal going to the Spark Max at all right now, right? So it's not telling it to stop. There's just no signal, and the Spark Max knows to stop the motor when there's no signal. If I tell it to run again, it'll be solid blue, but it is still stopped. So that's basically to say, okay, we are telling the motor to do something. In this case, we're actually telling it to stop, and it'll do that just fine. I can spin it by hand, like it's not trying to do anything different, but it is just not moving in either direction. We also have this graph up here. This graph is graphing the position of the motor. And since we haven't told it to move, this purple line is just sitting nicely at 0. And we can tell it for how many seconds it's been doing that. And so it'll start changing once we tell it to move. So I'm going to put in a pretty low number here. So I'm going to tell it to go like 0.1. So that's 10% of the possible speed, right? If 1 is 100, 0.1 is going to be 10. So I can tell it to run, and it kind of jerked a little bit, and then it's still spinning pretty quickly right now. You can't even really see the flag, but we can see that position number just skyrocketing. I can tell it to come back the other way. I can tell it to go even slower. Maybe I'll tell it to go 0.05. So now it's only going 5%, and it's going to go the other direction. So that's a little bit easier to see, right? It's coming back down. A little bit slower, but it's still going that other direction. Okay. All right, now we can start seeing it come back down. It went above the graph. It went above 40 pretty quickly. Okay, and so like I said, that's position. It is continuous, so it's monitoring it the whole time it's running. I don't think it's monitoring it when it's not running. I don't think so. Okay. Okay, so we can see a couple other things though. So this tool lets us have these signals, which is basically what it's plotting. So right now we've been plotting position. We can also we can plot velocity as well. So velocity is speed and direction, basically. So we can add the signal for that. Our graph up here changes a little bit. We get this other color on our y-axis. So we have velocity in RPM. So if I tell it, to start spinning up again and I hit run, we're gonna see it's doing a very small velocity. I can actually go in here and change this a little bit. So this is where we can set the scale. So this is like the max speed it can do is 5,800. So that's why it made those the top and bottom. But I can change this to something like like 1,000 and negative 1,000. So now we're a little bit, we can tell how fast it's going, and see the difference in speed a little bit. So maybe if I tell it to go to, whoop, that's a lot. If I tell it to go to 0.07, nope, what am I typing? It's not happy. 0.07, that makes it better. Okay, so if I run that, it'll flip it and have it start going the other way. So we can see it spun up a little bit faster. It was doing about 400 RPM or so at that speed. If we can make it go even quicker. So I'm going to hold it this time, because if I don't, it's going to jump. So if we tell it to go to 0.5, it'll run way up and just basically straight up off the page, right? Our scale was nowhere close to correct to see that. How slow it can go, we had someone ask. It'll go really slow. That's a good question. It'll get 0.01 or so. We'll still let it spin. It'll spin nice and under 200 RPM. Let's see, does it let it go to 0.01? Yeah, so that's about as slow. It starts hitting a friction limit right around there, and it'll start stopping just on friction itself. So 0.02 is about as low as it'll go right now, based on whatever that setup is. And that may be because this motor was used. A new motor may be slightly different, whether it has anything that we've changed on it and things like that. One of the things that we can look at real fast, we have this idle mode, either coast or brake. So right now it's in brake. If I switch it to coast, a couple things will happen. One, the light will change color. So now it's a pink light instead of a blue light. If I come over here and I tell it to go a certain speed now, when it runs and I stop it, it's going to take a little bit longer to slow down. So it wasn't too noticeable. There's not a lot of mass on it or anything, but it was slower. It is also a lot easier now. It's in coast. I can spin it with my hand really easily. When it was in brake mode, which I can put it back into brake mode, now it's harder. It's physically harder for me to spin it a little bit. It's just harder to get it accelerating. If I tried to spin it fast, it wouldn't let me. Because remember, brake mode basically uses the energy produced to try to slow it down. We had a question to see if I could tell to command it to go even slower. I don't think it's going to respond to that. We can see what happens. Yeah, the motor doesn't even know it's going anywhere. And so at that point, we're basically doing what's called stalling the motor. We're stalling it at a low enough voltage where nothing's going to happen. But if we did have something clamped to this or something and do the same thing where we had it, we were telling it to spin, but it wasn't actually spinning, it would start generating heat, which it can do for a little while, but at some point is going to either potentially damage the motor or hit one of the current limits inside the motor controller that doesn't let it keep going, depending on how we stall it and things. Okay, so let's see. So one of the other things we have a few minutes left to look at a couple other features. So as we start doing more interesting things, I'm going to pull the velocity signal. So we're only looking at position here for a second. And so what we're going to spend a lot of time next week looking at is that we have a couple different modes that we can use, one of which is position and another which is velocity. We also have smart motion and smart velocity. So the basic position mode allows us to change what our set point is. So before we were telling it a percent of our motor output, right? So our voltage input. Now we're telling it some amount of revolutions to go. I don't know if it's actually directly revolutions, it's position. I think it's close to revolutions if it's not revolutions. There's some way to convert it to revolutions if it's not revolutions directly, as like if it's native using it. So if we do this, if we tell it to go, let's see, our graph right now is up to 40. I can actually change that. 40 is okay, actually. So if I tell it to go to 20 right now, and we tell it to run, it will do nothing right now, right? We got no position, motor didn't spin, nothing happened. So the reason why nothing happened is that even though we told it a set point, we didn't really tell it how we wanted it to get there, right? There's a lot of different ways it could approach 20. It could go from here where it's sitting at 0 and it could get to 20. There are many different ways you can draw a line and figure out how long it would take and how fast you want to do it, how slow do you want to do it, how do you want to accelerate, how do you want to come back down. There's all sorts of ways to get from 0 to 20. So we have to basically tell it how we want to do that. And one of the ways we do that in the basic position control is with PID or PIDF. So these are these settings over here. And we can configure these, and we'll talk about exactly what all of these do next week. But basically, we can configure these, and you can start having an idea of how to control the motion of our motor in our system. So the simplest one is to add a little bit of P, and so P stands for proportional. Again, we'll talk more about it next week. So if we add just a little bit of P, so if I change this to say 0.1, I still tell it to go to 20. When I hit run, where are we at? Did I not reset something? Let me disconnect and reconnect real fast. I don't think it was actually at 0. So if you don't start at the 0, it doesn't work very well. All right, let me try that again. We can try 10. Nope, that's in percent output. That would be bad. All right, in position. Tell it to go to 20. If I tell it to run. Nope, that jumped off the chart way too fast. Okay, I think I need a much lower. I think I need a much lower P value. I think I forgot how low this had to be. I tested all of this earlier, but apparently not enough. There we go. All right, so our graph's coming back down. So we basically ran up too high, we ran way above because the P was too big. Now it's trying to come back down, and it's going to slow down as we start approaching the value it's supposed to get to. So it was spinning faster, and it starts slowing down and slowing down and slowing down. And it may actually, depending on how this value is, it may never actually get there. So 20 line is about here, and it's stopping before it ever gets there because basically our P value is too small. So we'll start learning what these, how these different settings actually relate to the outputs next week. But we can go in and change, okay, if that's too small, maybe I delete a 0. Now we're on a different order of magnitude, right? So instead of being 1,000th, we're up at 100th. And I can move it back to say, let's go to positive 20. We can run that. And so that got closer, right? So it spun up pretty quickly. And then we see this nice slowdown. We're pretty close to 20. Let's see where we're at. Yeah, we're at position 1909. So we're not quite 20, but we're close. And this is basically part of what we do when we talk about tuning a PID loop. A lot of what we're doing is editing these numbers, these like 4 numbers or so. There's a few others that we have to mess with depending on what we're doing. But we're basically just changing these ever so slightly to get the response we want from the robot. So if we want, one of the ones we have to do for a couple different years is to have an elevator go to a certain position. So if we started at 0 and we wanted the elevator to go to 20, we would figure out, okay, how fast do we want it to go to where we're going to hit that position precisely? It's going to stop cleanly, so it's not going to like stop too fast and break something if we decelerate too quickly. We're not asking too much of it. What happens if it runs into something? Like there's a lot of different things you kind of have to account for, but all of it goes into these different settings along here. So we can change it a little bit, maybe add slightly more P to it. If I add too much P, we'll see what happens there. Let me actually add potentially too much P. So instead of 0.1, let's go to 0.2. We'll go back down. You want to give it enough room to actually move. If I just tell it to go to 20 again from right here, it doesn't have a lot of room to move. So I'm going to tell it to go the other direction. It's going to drop. And so it's still cut off pretty nicely. I don't actually know if I can get it to. All right, let's see if I go too fast again. All right, it told me there was some sort of error. Let me make sure let me reset that and make sure I did it right. I may have had a typo. All right, let's see if we go back up the other way. Yeah, so this is so light right now, it may not actually let me. I'm gonna try to see if I can actually get it to go past the output. It doesn't seem to want to let me right now, but I also may just not be making this value big enough. We can flip it again. Let's see. Yeah, it's still, because since there's no mass on this output, right? It's just spinning its own shaft. It's able to stop itself really quickly. So I think I'd have to get it much higher. Ooh, that's way too high. Let's see. I mean, a lot of it is experimentation and just figuring out, not necessarily guess and check, but a lot of just searching to get something that looks too high or too low. Yeah, it's still able to just stop. Let's like double it. Let's see if that still doesn't do what we want. Yeah, I don't know if we'll ever be able to get there. So there's a couple different ways we can. If we start playing with some of these other settings, it'll do, they'll do even weirder things, so that the graph will change in even weirder ways. So I'd come back to one of our slow settings, and now we've added KI, which is integral, which changes things even more. When I tell it to run, yeah, so it just ran all the way out and then it came all the way back down. So now it's just like spiking back and forth. So it's a whole different, that's definitely not what we want it to do. If our robot was doing that, we would not enjoy it. So that's definitely something we don't want. So there's a bunch of different, we can figure out, okay, that setting wasn't good. It didn't help us improve. And we can change that through a variety of these settings. We'll look at the other control modes, position and velocity, and kind of walk through what these different terms are next week. And we'll look at what Smart Motion and Smart Velocity do. They basically just allow you to do some of the tuning a little bit easier, and they give you kind of smoother paths instead of these like what almost look like kind of straight lines. They allow them to be a little bit smoother on acceleration and on deceleration as well. So your robot just smooths out everything and it looks I don't know, almost more natural. I don't know, more elegant, maybe efficient. Less jerky is the big thing that they allow you to do, as part of what they allow you to do. Okay, I think that wraps it up for today.